Hello, we are here again with one more lecture session on multivariate calculus integration. Now, in the past two lecture sessions, we have seen the application of double integrals in finding area and volume. Today's lecture session, we will see application of double integrals in finding center of mass or gravity of a body. Now, I'm sure all of you know these terms center of mass and center of gravity. But still, let us revisit these terms once more. So, what is center of mass? The center of mass of a body is the point in the body at which the whole mass of the body is assumed to be concentrated. Center of mass of a body remains unchanged with the change in force of gravity. So, it depends essentially upon the quantity of matter. However, center of gravity is the point at which the whole weight of the body is supposed to be acting. So the center of gravity changes with the change in the force of gravity. Now note that in our case, as long as we are in the Earth's gravitational field, the center of mass and center of gravity will coincide because it's known that center of mass and center of gravity essentially coincide with each other when a body is present in a field of uniform gravitation. Now, the next question is that how to calculate the center of mass or gravity using double integrals. We will see that double integrals may be used to find center of mass or gravity of a plane lamina. However, if we want to find the center of mass or gravity of a solid, triple integrals will be needed. So that we can see later. At the moment, we will see application of double integrals in finding center of mass or gravity of a plane lamina. So first let us see how do we get the mass of a plane lamina with the application of double integrals. So let us suppose that we have a lamina which occupies a region R in the xy plane and is made up of non-homogeneous material. So let's suppose that its density at a point xy in the region R is given by rho xy. Then the total mass of the lamina may be expressed through double integral as double integral rho xy dA over the region R. And dA of course represents a elementary area or otherwise dx dy if we are in the xy plane. Next, the static moment of the lamina about the x-axis will be given by the formula double integral y rho xy dA over the region R, and we denote it with mx. Similarly, the moment of the lamina about the y-axis is my and is given by the double integral x rho xy dA over the region R. Now we can define the center of mass. So the coordinates of the center of mass of a lamina occupying the region R in the xy plane with the density function rho xy will be given by the following formulas. X bar equal to my by m, that means the static moment about the y-axis divided by the mass of the lamina. So that is double integral x rho xy dA over the region R divided by the double integral rho xy dA again over the region R. Similarly, the y coordinate y bar is given by mx by m, which is double integral y rho xy dA over the region R divided by the double integral rho xy dA over the region R again. So let us now apply this knowledge to some problems. And one thing, before starting problems, we should remember that when the density of the lamina is constant for all points xy in the region R, then the center of mass is defined only by the shape of the region. And in that case, it is called the centroid of R. Let's see now our first problem. Find the centroid of the lamina cut by the parabolas y square equal to x and y equal to x square. So as usual, let's draw the figure first. So here we have the parabolas y equal to x square and the other one y square equal to x, generating this lamina which we have denoted with r. Now to find the centroid of this lamina, we will apply our formula. And now see that we assume this to be homogeneous, and without loss of generality, let us suppose that the density rho xy is 1. Then the mass of the lamina will be given by simply the double integral dA over the region R, or otherwise double integral dx dy. Now for a moment we may think that double integral dx dy, we have earlier seen that it gives the area. But in this case it gives also the mass because we have assumed rho xy to be 1. And now to find this double integral dx dy over R, what do we have to do? Of course, we need to find the limits of x and y such that the region R is covered. So if we treat this as a type 1 region and vary y first, then we see that the lower limit of y will be in this lower curve y equal to x square, and the upper limit of y will be in this parabola y square equal to x, or otherwise y equal to root x. So here we can see in this integral we have put the limits of y from x square to root x. And what are the limits of x? We can see that the minimum value of x is 0 and the maximum value of x is 1, as this point of intersection of the two parabolas is 1, 1. So we now evaluate this integral. Now of course integral dy is just y, and as we put the limits from x square to root x, we get this as root x minus x square, and we integrate this with respect to x from 0 to 1. So as we integrate, what do we get? X to the power half, so it gives us x to the power 3 by 2 divided by 3 by 2 minus x cubed by 3. We put the limits 0 to 1. So finally, the mass of the lamina is 1 by 3. Next, what do we do? Next, of course, we have to find the moments about the x and y axis. So firstly, the moment about the x-axis, mx, this is given by the double integral y dA over the region R. We already know the limits, so we can put them. So y and dA, of course, is dx dy. So y dy, for the y we put the limits from x square to root x, and x had the limits from 0 to 1. So y dy, as we integrate, we get y square by 2. And we will now put the limits. As we put the limits, we get here x minus x to the power 4. So this is integrated with respect to x. So what we get? Half outside, x square by 2 minus x5 by 5. Limits are from 0 to 1. As we put the limits and simplify, the answer is going to be 3 by 20. Let's now find the moment about the y-axis. So my is given by double integral x dA, or rather double integral dx dy. Now we will again integrate first with respect to y. So it's integral dy going from x square to root x, and we have here x dx. So as we do this integration, we get root x minus x square x dx, that is x to the power 3 by 2 minus x cube, integrated now with respect to x from 0 to 1. So this gives us x to the power 5 by 2 divided by 5 by 2 minus x4 by 4. And as you put the limits and simplify, the answer is again going to be 3 by 20. So now the coordinates of the center of mass are given by x bar equal to my by m. So it's 3 by 20 divided by the mass, we remember we got as 1 by 3. So it comes as 9 by 20. Similarly, the y coordinate y bar also comes as 9 by 20. So therefore, the coordinates of the center of mass of the lamina in the question is 9 by 20, 9 by 20. Let's now see one more example, and now with variable density. So a plane lamina of non-uniform density is in the form of a quadrant of the ellipse x square by a square plus y square by b square equal to 1. If the density at any point xy be kxy, where k is a constant, find the center of mass of the lamina. So let's draw the ellipse first. So here we have an ellipse given by this equation. And the density is given to be kxy, where k is a constant. So to find the center of mass of the lamina of this ellipse, but mind it, it's for one quadrant. So let us consider the first quadrant only. Okay. So the center of mass x bar y bar will be given by, as per the formula, x bar is double integral x rho xy dA divided by the double integral rho xy dA. And of course, dA is the elementary area, nothing but dx dy. So what we now first have to find out are the limits of x and y such that the region R, which is the first quadrant of the ellipse, is covered. So if we treat this region as a type 1 region and try to vary y first, say that we need to take a vertical strip and the lower limit of y will be this x-axis, that means y equal to 0, and the upper limit of y will touch the curve of the ellipse. So from the equation of the ellipse, the upper limit is going to be b multiplied with root over 1 minus x square by a square. And x will vary from, of course, the minimum value of x is 0 and the maximum value of x is a. So therefore, if we just put the limits, the double integral appears like this. We have the inner integral as 0 to b root over 1 minus x square by a square, and x, in place of rho xy we put kxy, and this will be actually first integrated with respect to y, and then we will integrate with respect to x from 0 to a. Similarly, we get the denominator also, where it is rho xy, so it's kxy and dx dy, and these are the limits of y and these are the limits of x. Now, so far we have seen several problems and we have seen how to evaluate double integrals. So this will be your homework, and if you do these calculations, you are going to get the answer as 8 by 15a. And let us now see the expression for y bar, the y coordinate of the lamina. So y bar will be double integral y rho xy dA divided by the double integral rho xy dA. So the integrand is y, rho xy means kxy, and dA stands for dx dy. And we have the same limits for x and y as already explained. So y varies from 0 to b root over 1 minus x squared by a square, and x varies from 0 to a. So of course, we would first evaluate the inner integral with respect to y and then the outer integral with respect to x. And if we do all our calculations, the final answer is going to be 8 by 15b. So therefore, the center of mass for this first quadrant of the ellipse is having the coordinates 8 by 15a, 8 by 15b. With this, we will close today's session, and we are also over with double integrals. So in the next session, we will actually start triple integrals. Thank you and goodbye till then.